Greetings, gentle readers, fellow earthlings. Today is June 15th, 2026. Reading Foundations today with Ross Finlayson, myself, will be that the previous episode was about Mancosu's book, From Brouwer to Hilbert, The Foundations of the Debate in the 20th Century, the debate on the foundations of mathematics in the 1920s. Helping to give a clearer idea of what Hilbert's program actually is and what Hilbert's requirements actually are. Hilbert's program, of course, is the grand design of an idea of having a foundations of mathematics at all. One theory with all of mathematics in it. The foundations of mathematics, a foundation of mathematics. So from these selected excerpts and readings from Weyl and Hilbert and Mancosu and Brouwer particularly here, Hoelder for the Hoelder inequality after Cauchy-Schwarz, a triangle inequality in the functional analysis, a very similar sort of account. Bernays, known for Bernays and von Neumann and Goedel, taking an account of Zermelo-Fraenkel set theory and after-class set distinction, making for with or without Z of C with classes, having a second sort of elementary thing than sets in a set theory, but it's just classes being defined by their members, which is the usual inverse of sets being defined by being a member, or elt. Von Neumann and Goedel and Bernays, and variously called NBG or GBN for Goedel, Bernays, and von Neumann, have it that those then they have this schemified sorts of relations saying, once we start quantifying over these objects or elements and having to employ the actual axioms, then at some point in time we're going to need a schema, because otherwise we can't have everything be first order in the theory. So these are kind of the means of flattening what would otherwise become mounds and piles and infinitely high hurdles to hurdle. These are the kinds of things that the accounts then of reading from Bernays has a section, Hilbert's Significance for the Philosophy of Mathematics, on page 189. So perhaps that would help to describe a little bit more what's going on with Hilbert's program. Mostly known for Hilbert's problems, which are these either unsolvable things or unsolved conjectures of the time that were deemed to be of great foundational importance. And a few of those have been solved, and then some of those are some would say they've had developments made for them, but they're not solved. They're still open conjectures. These according to the mathematical independence, meaning that in the infinitary, there's both accounts when something is so and something is not so, and there, in fact, there's accounts of something is so and that the opposite is so. And so these are some of the examples of things that aren't paradoxes. They can't be paradoxes because mathematics is structure and form, but it's replete in its completeness, the continuity and infinity. Have it so. Then some of these problems of Hilbert have not uniqueness results, but distinctness results. And so that said, then a bunch of the Hilbert's problems are still open conjectures. And then the idea that they can be decided by variously laws of large numbers. Here there's being at least three laws of large numbers. The law of large numbers, the usual law of small numbers, that numbers are small, there's a bigger one. And then the law of larger numbers, which says, well, it's the law of small numbers is a law of large numbers, plus there's an arbitrarily much, much larger finite number that would then confuse or conflate or confound error terms or asymptotics, making for so that usual sorts of finite truncations fail. And then there's a law of the largest numbers, the idea being that, well, there's some numbers are infinitely grand, besides there being infinitely many of them. So just kind of a true infinite or actual infinite. These are these three sorts of accounts along are three models of continuous domains, each constructively established, each refuting each other according to inductive reasoning, but each made together after an account of superclassical reasoning the line reals, the field reals, the signal reals. 3 models of Cantor spaces, the square and the sparse and the signal Cantor spaces, and these sorts of things make for so that without those, then mathematics is sort of not only missing an opportunity, but missing a capability. And so having these is considered quite compelling and good, is the usual idea. From page 189, Paul Bernays says, if we look upon the intellectual relationships of the mathematical sciences to philosophy, as they have developed since the times of the Enlightenment, so the rational Enlightenment is when the reason came back to being after like the Dark Ages and the Middle Ages, and then the various feudal times before that. And then the Enlightenment and the Renaissance have the Enlightenment is kind of the recycling of the analytical tradition, and the Renaissance is the recycling of the idealistic tradition, and those being about the ontology and the teleology, the purpose of things, the causality of things. And so Bernays here is speaking about since the times of the Enlightenment. That's since the times of Enlightenment, since the times of scholasticism, since the times of the Islamic Golden Age, since the times of the Dark Ages and the Middle Ages, since the time of earlier scholasticism, Augustine, and then since the times of the rise and fall of the Roman Republic, and since the ancient Greeks, since before them the Sumerians and the Egyptians, since before that Anantha and the Atlanteans, since the times. We notice with satisfaction that at present mathematical thought is at the point of regaining that powerful influence on philosophical speculation that it possessed up to Kant's time, which it then suddenly lost completely. So this is about the strong mathematical Platonism and the idea that Kant's phenomenon and what's available in matters of sense, that being just an Epicurean account, and again, since Philo and Plotinus, but the Epicureans and those sorts of sophists, Neoplatonists, not really Platonists, having it that Kant's accounts of judgment and not reflecting upon ideals have that he does have certain ideals. For example, he has like in his judgments on virtue, or judgments on aesthetics, or judgments on his critique on pure reason. That's an ideal itself. And so once again, the deconstructive account of the analytical tradition is subject to its own deconstructive account to make a structuralist thing again, to be sensible again. And so saying that Kant had put away mathematical Platonism has here that something like Derrida reading Husserl on the Meditations about geometry has that Husserl says, hey, no matter what, we can never make a perfect circle in our minds, but I'm always going to have a perfect circle in my mathematics. And so that said here, what Bernays is perhaps alluding to is the idea that the formalism is making for point set topology, and then that suffices for his purposes. Let's see what some more of this says lately. That sudden averting from mathematical thought was influenced by the general estrangement from the spirit of the period of the Enlightenment that took place at the beginning of the 19th century. And I'd further comment that Kant has his sublime and the Ding-an-Sich, and then we can equip some basic numerological senses, an object sense, a word sense, a time sense, a number sense, and the sense of the continuum. This gives a reasoning agent access to the objects of mathematics and logic. Bernays continues, however, this detachment of philosophy from the exact sciences was only a unilateral one. Namely, while the dominant philosophy became quite estranged from mathematics, a philosophical orientation evolved more and more among mathematicians. The essential reason for this was that mathematics had grown far beyond the limits within which it had moved up to the time of Kant. Not only had the domain of investigated facts grown considerably larger, but the whole structure of the investigations became grander and the entire method more encompassing. So this is at once expansion of comprehension, and then as well, sometimes when it's about completions and the everywhere and the all and these kinds of things, then that's sometimes the almost everywhere and the almost all and these kinds of things. So while it is becoming more grand, as Bernays puts it, at the same time, some of these are due reductions and reductionism. So the generality for abstraction has that sometimes the abstraction is more grand and sometimes it's less grand. And sometimes making something more precise both gives a handle to the ins and outs of it, and sometimes it loses the handles to make it, to smooth things over. So it's just to be said that it's not a one-way thing. It's not a unilateral sort of account, as Bernays has put it. But it does speak true that the body of mathematics was growing in leaps and bounds. And not all the developments were old wrapped as new, but there were coming independent discoveries, and also the higher abstractions, higher geometry, and the relations between arithmetic and geometry in terms of algebra, and then these sorts of accounts. The essential reason for this, not only had the domain grown considerably larger, but the whole structure of the investigations, the concept formations, or Begriffsbildungen, Begriffs is like essays, and Bildungen is images, say. So the concept formations rose to a higher level of generality. The meaning of the formula became less important compared with conceptual abstractions and systematic fundamental ideas. Furthermore, the attitude towards the foundations, toward the object of the mathematical sciences also changed. The task of geometry was understood in broader terms. Geometrical concepts became more general and freed themselves more and more from the subordination to spatial intuition, the Vorstellung, the making points of things, making stars or points of things, Vorstellung. Moreover, in the recent geometrical theories, the intuition of space no longer had the significance of an epistemological foundation, but rather it was employed here merely in the sense of an intuitive analogy. That's nominalism for you, and fictionalism. And so the geometric connection to things is very much so about the equi-interpretability of statements of mathematical fact, and relating them vis-a-vis the integers and the integer lattice, the geometry and the linear continuum, and then the accounts of, here, for example, the models of continuous domains, the definitions of continuity itself, and these kinds of things. These are then the replete, making for the reticulum, the continuous manifolds, and the reticulum, and then for the concepts of Poincaré, it's like the Poincaré completion and stuff like that. That weren't necessarily available to this author in these times, and so his setting here is that he describes is like we're keeping geometry and arithmetic and algebra apart, and algebra is our rule, and so then as long as we frame things in terms of that, then it lives and stays in that. But the idea that geometry was somehow missing or whatever from things that are geometrical in their accounts in nature is not so. Geometry is the world measure. It is the account of space and objects and figures in space, or Husserl's perfect circle and these kinds of things. The task of geometry. In arithmetic, research experienced an essential extension of problem formulation as well. On the one hand, the concepts of number, the Anzahl, that's why they write the integers as Z, is for the Zahlen, the numbers, and of order, Ordnung, were, through the invention of set theory, generalized in a completely new way and applied to infinite totalities. So, set theory is descriptive about integers. And as among theories of one relation, set theory is a theory of one relation, and ordering theory is another different theory of one relation. So there can be order and ordering theories about inequalities or states of order. And then there's like sets and classes. So then about the infinitary, and then that set theory basically has the well-ordering principle. That's basically just given to accommodate and include that set theory is not an ordering theory, and ordering theory is not a set theory. But they're both fundamentally elementary theories of only one relation, Elt for set theory and less than for an ordering theory. And so Elt and LT, their habits so that they're different theories, and then those being equi-interpretable for each other, then have all the paradoxes of quantification, induction, identity, infinity, and continuity would live in either one of those. The numbers are just descriptive in those. Numbers are like, these are the modular, integral moduli that make the integer lattice, and so give the natural whole counting numbers, vis-a-vis geometry's account, and algebra's description also thereof of those. That what Bernays is describing is an account of formalism and abstraction is the nominalist fictionalism. And so for mathematical Platonism, this is like somehow they still all live in one theory. So the idea is that a heno theory is a theory that's like, I'm a theory and I have only one relation. But in it, I make models of theories, other theories of one relation and all their structures and results. That's what a model is. It's got all the structures. It's just are all the facts, all the relations so exist. And so having that for set theory and ordering theory and then putting them together and saying it's like, well, now it's more abstract in general. It's like, well, yeah, but there's another one just like it that's entirely different. And so trying to figure out then what's like a one-line proof in one theory, and it's like an infinite series super deductive result in another theory. That they're equi-interpretable still, but then according to the various ways and these kinds of things. On the other hand, the development of algebra led to numbers and quantities no longer exclusively viewed as objects of investigation. Rather, mathematical formalism itself was made an object of study. One focused very generally on the examination of formalisms. Numbers as well as quantities now appeared only as something special. And the more one examined their lawfulness under more general points of view, the more one became unaccustomed to taking this lawfulness for granted. So that's a yes and no, because for accounts of intuition, like, well, half of the integers are even, but the cardinal numbers of the infinite collection of odd numbers and infinite collection of all numbers is the same. And so in one sense, then the accounts of ordering and size and relation and these things with regards to numbers and the infinite totalities there still exists density of numbers and asymptotic density or Schnirelmann density for giving the fact that half of the integers are even. And while at the same time that for Galileo's paradox or cardinality, and the transfinite cardinality and the countable sets having the same size and not being able to say that they're different as sets, they don't have any other relations at all. But as numbers, they do have other relations. So at some point in time, you can't just say, oh, I've defined numbers and I'm going to treat them as sets absent all their numeric relations, because then they wouldn't be the numbers. And so a usual account that will give something like, what's Peano's numbers? He says, well, there's 0. And then there's a successor of 0. And then, according to induction, there's a successor of that. And this gives as the same as an inductive set, meaning 1 and the next ad infinitum, infinitely many. That's a way to give an account of an ordering and ordinals, but to give numbers, it also has that, 4 minus 2 is the same as 2 minus 0. Because otherwise you could say, well, it's just an infinitely many and they're all less than like a magnitude. And that like one only gets half the way there and the next only half and half and half and half again the way there. And so defining those as numbers without giving them a space to live in already is a bit too simplified. And so Peano's definitions then for arithmetic and addition and multiplication and subtraction and division. Here besides the deconstructive account, there's like increment is primary and partition is primary. So we get the operation of addition one way like the Sumerians, the operation of division the other way like the Egyptians. Yet they result in the middle after all the relations exist, the integers on the real number line. This has that Bernays is talking about things that were due loose language and the ambiguity. Something is ambiguous, it's not clear which of either two things it may be, or if it's one or the other of them at all. So the disambiguation after the abstraction and generalization, things like it's all sets in a set theory, has that model theory demands that a model, to be a model of something, has all the structural relations that it has. And so that could help solve Bernays' problems here because he's made them himself. In this way, the whole development of mathematics moved on to rob of its appearance of exclusiveness and finality all of that which was previously considered to be the only object of research, and whose basic properties were considered as something to be accepted by mathematics and neither capable nor need of mathematical investigation. The bounds the previous philosophical view and even the Kantian philosophy had marked out for mathematics were burst. Mathematics no longer allowed philosophy to prescribe the method and bounds of its research. Rather, it took the discussion of its methodological problems into its own hands. In this way, the axioms of the mathematical theories were more precisely investigated on the basis of their logical relations, and the forms of inference were subjected to more precise critique as well. And the more these problems have been pursued, the more mathematical thought has shown its fruitfulness with respect to them, and has proved itself an indispensable tool for theoretical philosophy. David Hilbert has contributed in a significant way to this development, which extends to the present. What he has accomplished in this field will be described in what follows. So, saying that there was or is an account of the formalism in mathematics, and to be dealing with the logical objects is, well, obviously enough, logical objects and mathematical objects model each other. Like, for example, making Boolean algebras from yes, no, or true-false relations in logic, or from making arithmetizations or geometrizations of objects according to their logical relations, the relations. So relation is omnipresent in structure and the whole model of the things, the universe of mathematical objects. The domain of discourse, the language about it, the universe of mathematical objects which exists. So saying that Kant said that, well, the universe doesn't exist anymore, you can say whatever you want, and whatever you're saying is the domain of discourse, and it also happens to be the universe of mathematical objects you're talking about. People would just call that worlds instead. It was like, well, this is just my world. So before the multiple worlds interpretation, the pluralistic fragmentism of the synthetic gap accounts of the sorts of people who have to like put two theories together that break each other, has instead here there's still just one good theory, and then the abstractions though exist and live on it. So even all the accounts of disambiguating things and making projections and conjectures is free, and those just all live as examples of objects, and whether they model theories or not, structures in relation or lack thereof, and do or after disambiguation for predicates and disambiguating quantifiers mostly, about the transfer principle, when something's so for each, whether it's so for all, and those being different, for each, for any, for every, for all, that these sorts of accounts do live in the logic, and they're about infinity and continuity, and the very most utterly fundamental terms, the terms, and the predicates and propositions, and then about relations, and these sorts of accounts. David Hilbert. When Hilbert applied himself to the problems that were to be solved concerning the foundations of mathematical thought, he had at his disposal not only his comprehensive command of the mathematical sciences, but he was also, above all, as it were, predestined for the task by his human disposition. Mathematics had for him the meaning of a worldview, and he went about these fundamental problems with the attitude of a conqueror who endeavors to secure a sphere of influence for mathematical thought that is as comprehensive as possible. So that's usually given to expansion and comprehension. Mathematical objects exist, and so it's not for anybody to say that they do or don't, but it is for anybody to say how they do and how they don't in the language that's interrelatable or interrelatable, or at least to be the sensible, fungible, and tractable, makes mathematics what it is. And then sometimes there's considerations like, where does the word root math even come from? Logic, I guess, comes from logos, the word. And there's the idea that math is like this Egyptian figure Ma'at, M-A-apostrophe-A-T, Ma'at. So Ma'at and math kind of have this kind of idea. And then there's also Anantha, and that condition and tradition of the prehistoric tradition of the objects of mathematics, which have been part of human language since before all the accounts even arrive, beyond the written tradition at all. And so these are ways to make for so that then when we're talking about formal theories that are simple and like pick them up and put them down theories, as I call them, like it's like you can just pick up this crossword and solve it and put it away when you're done, or and pick it up and put it down, and pick it up and put it down. And when you're solving another one, you don't need to limit them to each other and this kinds of things. Still has that as objects of mathematics. They all live in a one domain of discourse, a one universe of mathematical objects. It's called Platonism, and it's called mathematical Platonism, after Plato, one of those ancient philosophers. In the pursuit of this goal, the main point was to avoid the mistake of those extreme rationalist thinkers who thought that a complete knowledge of all that is real, alles wirklich, could be attained by pure thought. See, I do. I think that if that makes me an extreme rationalist, well, here it's just a mathematical Platonist who's, as a logicist positivist, has to come to terms and grips that after naming objects for the theories, that all the paradoxes have to be resolved for them. And so somehow thought does that. I think that's a great idea. And so that's alles wirklich. Then saying that to give all that's real of that, though, is quite a big gap from saying, like, here's the foundations, and here's a model of geometry, and here's a model of arithmetic, includes the non-standard and superstandard, the Euclidean and the Archimedean, from nothing else. Not even, we're getting axiomist geometry to give Euclid's geometry. We're getting an axiomist arithmetic to give Archimedes' and Eudoxus' and so on, arithmetic. So that said, then it can only be attained by pure thought and lots of diligence and in the expansion of comprehension, having seen out all the different trails of the expansion of comprehension. Bernays continues, this could not be a question of, say, including in mathematics all knowledge of the factual, tatsächliche, a word I'm not so familiar with. I know wirklich, I don't know tatsächlich. Including in all mathematics all knowledge of the factual, so that would be the ontology. And so some people think that, oh, well, if I knew every single fact, then I'd know every single thing in reality. It's like, well, I guess it kind of depends on how fast you can recall and compute. And then the facts change. And then there's the model of a modal temporal relevance logic. Has that there are many breaking points in that sort of account. But the ontology otherwise is just the fact base and the knowledge base of somebody. Rather, it was necessary for the purpose of the widest possible extension of the domain of mathematics to undertake a sharp delineation of boundaries between the mathematical and the non-mathematical, which would actually allow one to claim for mathematics all mathematical components in cognition. Alle mathematischen Bestandteile im Erkennen. All the mathematical Bestandteile, the accounts of holdings or standings, im Erkennen, of knowledge. Hilbert was actually also understood the problem in his way, in this way. Hilbert has actually also understood the problem in this way. His first and largest work in the field of methodological questions is The Foundations of Geometry, which appeared in 1899. In this work, Hilbert laid out a new system of axioms for geometry that he chose according to the criteria of simplicity and logical completeness. Following Euclid's concepts as closely as possible, he subdivided the whole system of axioms into 5 groups of axioms and then investigated more precisely the part that the different groups of axioms, as well as single axioms, have in the logical construction of geometry. So Hilbert's postulate of continuity basically says that, well, you know how it is that points don't make a line and lines don't make a point? Well, here's a postulate of continuity that points do make a line. And so for Hilbert to put this forward in his Foundations of Geometry as an axiom, it's a stipulation. He's like, I can't really say it one way or the other because it would contradict itself. All I'm going to say is that anytime you ever consider any possible fact in this theory, Hilbert's Foundations of Geometry, it always has a postulate of continuity. And so it's possible that then the point sets make a line and making a structure of it and a model of it. Now, is that always so? It's like, well, yes and no, because mostly it would be considered not so. Because there's points are not lines and lines are not points. But here that's the same thing as line drawing, or that the spiral space filling curve forms a natural continuum in the infinitely many dimensions at once. It also forms the dimensions and the continuum. It's just this great growing ball of continuity. And then the linear continuum is just like a line through that. That is a straight line determines the shortest distance, and a shortest distance defines what is a segment of a straight line. And so these sorts of accounts have that. Hilbert added the postulate of continuity because it's otherwise just Euclid's usual axioms. And then that's kind of what is going on in that. Through the wealth of new fruitful methods and viewpoints it presented, this investigation has exercised a powerful influence on the development of mathematical research, meaning it helped connect geometry with algebra and the accounts of the objects being elementary as points, for points. However, the significance of Hilbert's foundations of geometry by no means lies only in purely mathematical contents. What conferred popularity on this book and made Hilbert's name renowned far beyond the circle of his colleagues was the new methodological turn that was given to the idea of axiomatics. The essence of the axiomatic method, that is, the method of logically developing a science from axioms and definitions, consists, according to the familiar conception, in the following. One starts with a few basic propositions, Grundsätze, so the ground settings. The Ansatz is like the setup or the thought experiment. Or the Gedanke is the thought experiment, and the Ansatz is the setup. So the Grundsatz is like the setting. And so from Frege was like the Grundgesetze, the ground laws in these sorts of accounts. So this is foundations, is what they're talking about. The Grund, the Alaya, the foundations, all being the same kind of term. The base, the firmament having a place under this fundament, or vice versa. That these are what the basic propositions are would be in this account of Bernays about Hilbert. That this is the axiomatic setting. So then this is also the same thing as positivism. Positivism is like I posit an axiom or a theory or a hypothesis. It's positivism. And then logicist positivism is like and is connected to logic, meaning it's only connected insofar as logic is connected to it and it's connected to logic. It's not necessarily connected to the real world. It's a pick them up and put them down sort of theory. Logicist positivism. So connecting again the mathematical Platonism with logicist positivism is great exercise in foundations because there already is one, or else there would be no perfect circle or straight line. So these are the sorts of accounts then that, again, at the time where this is going on, then by now there's also the postmodernists and deconstructivists or Derrida, and then reading Husserl, who being these strong logicist positivists, have that, first of all, that their ideals are that, it's not that they're absent ideals, their ideals still are that, but then also that the accounts of keeping those distant yet coherent gets involved, and that many just leave it off as that. There's a usual joke that people say is like, well, so-and-so a mathematician is like, what kind of mathematician are they? Are they the formalist or constructivist or an intuitionist? And a formalist meaning it is like everything has got to be all the way down to the ground, every single fact, explicit and all consistent together. So the usual idea is a mathematician is a formalist 6 days a week and intuitionistic on Sundays, or vice versa. Or meaning it's like they to claim the authority of something being verified as being certified, it's got to be all the way to the ground, how it's known, how it stands up. It's got to have visible means of support all the way up. And so then the idea usually is that mathematicians don't think of that at all. They think in terms of their own ansatz, their own settings, of what they're working with, and their theory, their objects, whether that's programming computers and working with an object-oriented model, whether it's working with theories of types, whether that's working with anything that's theoretical at all, and then the practical about how it's applied. Most people don't care about the foundations. And indeed, there's a great rift between like atomic physics, quantum reality, and the general relativistic space-time continuum, and stoplights, or reading the mail or something like that. That while that's involved and has it so, then the axiomatics comes out of it. Then the axiomatics itself is a lot the same since the time of Euclid, and as Proclus put it, for quod erat demonstrandum, it's so demonstrated, and quod erat faciendum, it's like, well, it's not wrong, and it's a lemma of this other sort of account, as it would be. The foundations then is a really diligent account to arrive at everything. Then figuring that you can give axiomless geometry and give axiomless arithmetic, and then also an account of the non-standard for continuity and infinity, because it has those. Then that's figured a good theory overall. And then if it avoids axiomatics, that's also good, because any axiom you add, the ancient Greeks will say automatically, no, that's negated. You just can't say anything at all about the objects of mathematics. A person, an individual, just can't say anything at all about them, because that would not be humble. It's like they exist a perfect circle in a straight line no matter what. So the account here of getting into axiomatics in this framework and saying we are working in these settings, and so we can say what we want to say, and you can't say otherwise. That's fine. It's a pick them up and put them down theory for a plank or a platform, but foundations is a bit more proper, the term. In this view, Bernays continues, attention is focused above all on the epistemic character, the Erkenntnis character, the knowledge, the knowingness, the character of the axioms. Indeed, originally one recognizes axioms only propositions whose truth would be clear a priori, and still Kant held the views that the success and the fruitfulness of the axiomatic method in geometry and mechanics essentially rested on the fact that in these sciences one could proceed from a priori knowledge, the axioms of pure intuition and principles of pure understanding, Verstand. So that's that's the principle of sufficient reason and the principle of sufficient and thorough reason, and then that's usually given to Leibniz. The principle of sufficient reason is like, this suffices, it's enough. I need all the reason I need, and this is it, and this is enough. But the principle of thorough reason is, furthermore, is like, and all the possible disambiguations have been made, and all the possible paradoxes have been resolved, and it still suffices to not fall under itself. So that said, then, saying that this axiomatic account said, well, we can talk about the algebra and whether or not it's the numbers, or like simple, very, very simplistic simplifications, and say we're talking about the real deal. Yes and no, because from inside the theory, there's inductive ignorance, it's willful ignorance, but from outside the theory, it's not. So this demand that each axiom should express an a priori noble truth was soon abandoned, for in the manifold occasions that presented themselves for the axiomatic method, especially in the further development of physics, it followed, so to speak, automatically that one chose both empirical statements and also mere hypotheses as axioms of physical theories. So the empirical statements and the formal methods also had to build on the whole stack of derivations. So as it comes along, that by the time that somebody was talking about pendulums and trying to figure out how to apply it to models of diatomic molecules or something like that, Hooke's law about pendulums, getting in the Clausius and Arrhenius, the models of the things had already built in these reductions that have truncations or approximations in them that have lost some of the character. So there's implicits, the behavior and the character that's just lost. Like Galileo doesn't say anything at all about spinning bodies. He just says, I don't know anything about it. And so he doesn't. But anything that comes about after and out of that has said, well, they're perfect inelastic collisions. It's like, no, there's not. No, or you may examine and validate for yourself, as I have for myself, and feel to be verified and validated. There's room in the theory, of course. That finding where the room in the theory is, like in revisiting Hooke's law and Clausius and Arrhenius, Planck, Kelvin, and these sorts of things, have it so that otherwise they're just buried in the stack. And people who are building on that, like, it's like, I got the definition momentum since Newton and Leibniz, often say Leibniz, and that's how I learned it and always heard it growing up. Newton and Leibniz were fighting about vis-viva and vis-motrix, vis-a-vis vis-insita, the active force, the rectilinear force of Newton, and the vis-insita, which is like, well, what happens at collisions and stuff like that. Because obviously, the developers, the philosophers of mechanics using mathematics knew that there are issues, but this is what they came up with that at least got a grip. They made something sensible and then fungible, and then to make it tractable. Then the more fully thorough then gets involved in these sorts of ways. About what is an a priori truth, vis-a-vis what is an assumed axiom. The axiomatic procedure turned out to be especially fruitful in the cases where one succeeded in encompassing the results of multifarious experiences in a statement of general character through the positing of an axiom, sometimes laws. A famous example of this is the two propositions about the impossibility of a perpetuum mobile of the first and second type, which Clausius put at the top as axioms of the theory of heat. So when I'm talking about Clausius and Arrhenius, it's not necessarily so as about the adiabatic, but that is a part of it. And so then that relating things like Maxwell's demon and stuff like that, which is the idea is like atoms move in a random manner, and but their energy is and their heat is defined by the energy they have. So the slower ones are colder and faster ones are hotter. So if you could have a gate and then they have a little demon called Maxwell's demon, and it's sitting there, and whenever a slow one comes, it opens the gate and it cools in, and whenever a fast one comes, it closes the gate and it bounces off, so that it would move the heat into one chamber vis-a-vis the other. Has that it's so that according to materials, you can still make a Seebeck or Peltier junction, and that's how a refrigerator works. You know, it's cool on the inside and hot on the outside. Yet at the same time, it's like the whole world gets hotter by keeping that going. That there's no perpetual mobile in the closed, but in the open, that's the usual kind of anything that's dynamics at all. So that said, it makes for accounts of the diabatic and adiabatic, the usual accounts, and then for heat and chaleur, and the models of things like, well, we're just going to have a fluid model of flow, or we're going to have a model of pneuma for the air and the gases and these sorts of things, or the accounts of chaleur for heat, or till basically they just got to like heat and flow, and then the liquid models for liquids and electrical models for electricity, both fluid models, with various things that are entirely contradistinct, where then a law would apply to say, like, this electrical circuit is just like a waterfall, whereas another one says, like, this electrical circuit is entirely opposite how water works. So when these axiomatic theories or is about laws, they only apply in the regimes, in their systems, and with regards to open and closed in physics and this kind of thing. Moreover, the belief in the a priori knowledge of the geometrical axioms was increasingly lost among the researchers in the exact sciences, mainly as a consequence of non-Euclidean geometry and the persuasiveness of the arguments by Helmholtz. So Helmholtz has got here with the spiral waves and wave spirals, and that's also Duke Kelvin, who's got a theory of vortices. It's unlinear. And then since Descartes' it's subtle matter, his own sort of set of laws and axioms that better described at least some characterizations of mechanics, unlinear. That the account that is like the current mass market standard account is very linear and it's much simplified, but it's got all kinds of places besides in the stack of derivations mathematically and algebraically. Also, each of these different fields in the empirical settings, they then diverge and get diverted into their own particulars. Because otherwise the law that stands up in the middle is so great that then says, oh, finally we can just concentrate on one aspect of an apparatus of analysis that will work on all these different things. So I don't have to learn 10 different mathematics and get 20 different mathematics degrees to do 3 different things. I can do most of things like Pareto law, Pareto law, the 80-20 rule, is like I can do most things with like a sufficient set of tools, and then what I'm left with, that's for particulars to sort out. And that said, it is a great strength, but at the same time, that's just for kind of bringing an even keel to everybody that working in the field of the linear curriculum to get to the linear developments, so that then you can arrive at somebody who's already familiar with the tools to then get into the specifics. And then talking about the geometrical axioms and saying this, like, well, we're talking about the fourth dimension now, and time is relative. And so we're going to say that the fourth dimension exists and that it's out. And so things could just pop in and out of what otherwise would be a system of the world. That's yes and no. And then with regards to, like, well, we just got to be able to model torsion, and how could that be that something could spin in a world that's continuous, because it would tear. It would either make a twist that would infinitely twist something just to spin once. And we know from like a string or anything else that if you twist it enough times, it will break. So that would make the discontinuous out of the continuous. It's like, well, actually it just kind of does that, and then it relaxes somehow, it reforms. So for the accounts of space frames and frame spaces and real space contraction, is there's something going along, it kind of like compresses the wave in front of it and relaxes the wave behind it and moves through space and these kinds of things. Or that if it spins and it's rotational, that the world spins around it. And how that can be that it's not discontinuous and needing an account of non-Euclidean geometry, which essentially must at some point either mean beyond the infinite or discontinuous. Here's that everything is continuous. It's the space-time manifold, the continuous manifold, and all the field theories agree. So at this time, and talking about the idea of the fourth dimension is saying, it was like, well, now this is why we've lost attachment in mathematics. It says, like, this is why we've gained attachment to a greater account of mathematics. So again, Bernays could be kind of placated by this sort of reasoning. Non-Euclidean. Thus, the empirical viewpoint, according to which geometry is nothing but an empirical science, found more and more supporters. So this is the idea that mathematics is a science instead of that for mathematical Platonism, that it's a study of the objects of mathematics. It can be both. Anybody really has a science of mathematics, but it's the science of the theory of mathematical objects, not the science of, not like the science of apples and pears and bumblebees and fruit flies and stuff like that. Vis-a-vis their organism and organization and cladistics and phylogeny and all these sorts of accounts, the ontology of their being, a science, and the statistics about them, a science, and the science about them, statistics. It has that the theory of mathematical objects is about these are mathematical objects that are perfect circles and straight lines. They're true. And so, again, that's not shared by all, even today. It is widely held, though. That's the usual point of logicist positivism, that they're nominalist fictionalists and these days fragmented pluralists, because by now everybody's found at least one paradox or contradiction in what they were given. That resolve in those is the idea of the theory. For a paradox-free reason, and a theory where there's only one paradox, there are none, that being the no paradox theorem. However, this departure from a prioricity, from a priorismus, did not essentially alter the view under which one considered the axiomatic method. Well, no, not at all. A more powerful change, however, was brought about by the systematic development of geometry. Mathematical abstraction had, starting with elementary geometry, raised itself far above the domain of spatial intuition and had led to the construction of comprehensive systems, in which ordinary Euclidean geometry could be incorporated, and within which its law-likeness appeared only as one particular among others of equal mathematical rights. With this, a new sort of mathematical speculation opened up by means of which one could consider the geometrical axioms from a higher standpoint. It immediately became apparent, however, that this mode of consideration had nothing to do with the question of the epistemic character of the axioms, which had, after all, formerly been considered as the only significant feature of the axiomatic method. Accordingly, the necessity of a clear separation between the mathematical and epistemological problems of axiomatics ensued. The demand for such a separation of the problems had already been stated with full rigor by Klein in his Erlangen program. So Klein is considered a great. He wrote like a history and a dictionary, if it's the same Klein, or Etienne Klein, I'm not sure about that. The Erlangen program is way before like the Langlands program. The Erlangen program is before or around the time of the Hilbert program. The Erlangen program is considered good. I need to look at that some more, the Erlangen program. But here it just says, Klein says, there are problems, so that's clear. There are those to be disambiguated and resolved. Here, Bernays says, the important thing then about Hilbert's Foundations of Geometry was that here, from the beginning and for the first time, in the laying down of the axiom system, the separation of the mathematical and logical spheres from the spatial intuitive sphere, and with it from the epistemological foundation of geometry, was completely carried out and expressed with complete rigor. It also lost connection to that. To be sure, in the introduction to his book, Hilbert doesn't express the thought that laying down the axioms of geometry and the investigations of the relationships is a task that amounts to the logical analysis of our spatial intuition. And likewise, he remarks in the first paragraph that each single group of axioms expresses certain related basic facts of our intuition. And so Husserl also says this. And then also, I was just reminded of an account from the reading of last time from Hilbert about how he also makes a very strong account about like the real numbers, and saying the real numbers have got to have at least all their character included in these kinds of things. And so it's similar with his concept of geometrical intuition. That it's like, well, we can't be making axioms of geometry that haven't, like Euclid's, survived forever. And because they're not just for the scientific account, but they're true in all sorts of measurements, but also that abstractly vis-a-vis accounts of minimality and maximality and congruence and these sorts of things, that there are all of these sorts of axioms, and they're always so for objects of geometry. Then about the parallel postulate being let out, that's like that's ad infinity. So the only thing that anything could change about Euclidean geometry is like ad infinity, and then the only way a torsion or a twist can happen in a continuous manifold at all that's complete is taking that infinity and shrinking it into a box, and then now treating it as its own, not a world, but as a frame space in a space frame here. That is still as continuous, is what I'm saying, and then that how it gets there is accounts of reflection and rotation and these sorts of things have that it does. So yeah, that definitely matches most everybody's spatial intuition that turning around a complete circle results facing the same direction. So these are usual sorts of accounts that everybody has naturally. And then to gain this extra spatial intuition, that is learned, and it's a significant point of abstraction and higher thinking to begin. So when I say that it gets back to being like a single theory that's coherent and altogether and paradox free and this kind of thing, that's in no way to prevent that. Otherwise, to get there, anything is abstract. Nothing is continuous. The whole world is contingent. There's entirely infinitely many worlds of theory. All that is could be anything at all. Furthermore, when we get to the abstractions, then to apply the dialectic and the reasoning agent's apparatus is always being able to make examples of everything and not just be stuck in the middle with them, which is then the other usual account of being in Kant's world, just like under our senses. That having a mental sense is like it's infinite, continuous, and free is the idea. And then how that gets to be so in the actual whole universe of mathematical objects is a separate thing. So axiomatics is just rationality and abstraction. The rationality isn't just following the axioms, but thinking them over and making the knackabout of the ideas and thinking about things, not just thinking something, thinking over something. That by all means, Bernays' account of Hilbert's account of Klein's account of getting abstract about that is critical to being critical at all. But then getting back again to this paleoclassical, we studied the archaeology of it, postmodern, again, it's been deconstructed, it's been torn down, finds itself back again as structuralist realists. That's the holistic account of the more thorough variety. To be sure, in the introduction to his book, Hilbert does express the thought does amount to the logical analysis of our spatial intuition. Of course, demands have always been placed upon a rigorous axiomatic grounding of geometry that the proofs should exclusively appeal to what is formulated in the axioms and must not rely upon spatial intuition in any way. Well, if you give that as an axiomist geometry and give everything that comes from spatial intuition in that, then it's already there. So the idea that like a theory is like, well, this is in the theory. You can't talk about anything that's not in the theory. It's like, well, any meta theory includes that, and any meta theory of that includes that. And theory in itself includes all those, even as examples of two different theories not agreeing. So while it's so that you can't appeal outside of the theory from within the theory, from outside the theory, you don't have to ignore other aspects of the theory. And so when it works out, it's like, well, actually my theory is that this other one makes a logical paradox of my theory, but I'm using Hilbert's postulate of continuity that these points make a line. And so if I don't, then I don't have one, because Russell told me I would be wrong. And so these sorts of ideas go to show that having it so that it's contingent is like, well, no, you still look at the theory within itself as it must be perfect and pure itself, and they must somehow disambiguate all the elements in the one theory and all the elements of the other theory that may either disagree or make it disagree, and then still keep examples of those. Then for the judgment and the stroke, saying this decides which of these is so and what holds, is for over on account of a true theory. And then for what axioms or principles or laws those are that hold, that make that so, these are very good ideas. Must not rely on spatial intuition on any way. They must make the spatial intuition in all ways. More recently, Posh, in his Foundation of Geometry, has placed importance on the carrying out of this demand and has been completely consistent in doing so. That's arguable. Because to be consistent, he can't be consistent and complete according to Gödel. However, Hilbertian axiomatics goes one step further in the elimination of spatial intuition. Reliance on spatial representations is completely avoided here, not only in the proofs but also in the axiom and the concepts. The words point, line, plane serve only as names for three different sorts of objects, about which nothing else is assumed directly except that objects of each sort constitute a fixed determinate system. They are points. Any further characterization is carried out only through the axioms. In the same way, expressions like the point A lies in the line A or the point A lies between B and C will not be associated with the usual intuitive meanings. Rather, these expressions will designate only certain at first indeterminate relations which are implicitly characterized only through the axioms in which these expressions occur. That is one way to look at formalism, saying it's like, we need to be able to write this in a program that we can then put on a machine and use it to crunch. And so we can't make any kind of appeals, suggestions, or prompts to it, saying it's like, also apply mathematical spatial intuition here. It has to have that all encoded in the system. So that's saying it's like it's not so much saying that this axiomatic method frees us and lets us just ignore anything else. It says this axiomatic method requires us to fulfill all the possible things that come out of these axioms alone. And then the idea is like, well, can a system give us the axioms of geometry, the axioms of arithmetic? Then I guess I can do arithmetic and geometry with those. Like this axiomless geometry and axiomless arithmetic. to arrive as Bernays put it, the extreme rationalist position, that the objects arise from the point in space itself, from nothing, the void and all the universe itself. So these are usual enough things, and they've been around forever. Well, let's see. That's been reading a few pages since page 189. That's page 192, and then it's been about an hour or so. So what I suggest is that Bernays then has his counts in formalism, where he also puts his name with later with von Neumann and Goedel about an account of set theory. I mean, he found something that would make a paradox, or otherwise break something that they're trying to keep simple. So NBG is usually enough. ZFC set theory. Or GBN or NBG is not different than ZFC set theory. Then ZF with classes, or ZFC with classes, those are different. And NBG, now sometimes people say NBG or GBN set theory, and say that that's with classes for class set distinction and proper and ultimate classes and the like. And usually these days, that's always a given. I mean, the usual setting of the analysis of set theory always has classes as a descriptive term, and indeed even a primitive to sets, so they can talk about sets, and otherwise this meta theory. So long story short, that was an interesting selection that Mancosu found that helps to explain then when Mancosu is talking about things like how many points are in this line, and how many points are in a line that's twice as long, and then being able to say, well, since Grosseteste and aliquot parts, we can talk about ways that their density is going to differ, and then since Galileo and Cantor and Cardinale, we can talk about how they're the same, and there are both of those accounts, and then whether they're just sets, points in the set theory, or whether they're points in a geometry, then gets into that. Geometry is the world of geometry. Arithmetic is the world of arithmetic. Algebra is the world of algebra. And theories of one relation are just very fundamental and elementary. And there are more than one of those. Warm regards, gentle reader. Very warm regards.